Um, Good morning, everyone. My name is Dehan, and I'm representing the Belipola Arboretum and Research Center as the managing director. It's a great honor, really, to be here and to be in this era concerned with nature and our association with it. The association spans from how nature can benefit us in our health and our living, as well as how we can develop landscapes and businesses into the future. Belipola Arboretum was inaugurated, concept of applied forestry, thought about by Dr. Ranil Senanayake. Dr. Ranil worked within a myriad of ecosystems around the world. He studied them and he came to Sri Lanka to demonstrate that we could integrate this knowledge of plants and species and ecosystems to generate degraded landscapes across the world. So Belipola Arboretum was the project, analog forestry at Belipola, was inaugurated in 1980, 81 thereabouts. And the project had inspired many international students, as well as professors from many universities, to come and visit this project. And today, 40 years later, we have one such student who was then captivated by the project, followed the founder, Dr. Raj, and was able to articulate his own methodologies for inspiring young generations into more sustainable land use, land management practices, as well as integrating technologies into this science. Now, with that brief history, I will introduce you to what is the current context at Belipola as an arboretum and the presentation will be very brief. It will be about 8 minutes. I ask that all of you attending this session here today, please to mute your microphones so the session and this information that is being shared. I also ask that all of you take the time to toggle through and find the chat window, and please sign your name so that we can connect past these lectures. All right. So for all of you in attendance now, I'm going to share with you a little bit about the current context of Belipola. Please give me a moment. Okay, so Belipola Dialogues, the first edition, we are going to discuss landscape topology. Landscape topology as a subject will be introduced to you by Professor Christophe Giraud. He is a professor who is visiting Sri Lanka after 40 years and is the chair of the Landscape and Architecture faculty at the MIT of Switzerland, ETH Zurich. So before that, we will carry on to identify a little bit of what we know about landscape topology. Simply put, it is the three-dimensional or even four-dimensional study of biophysical and biochemical interactions that are present within a landscape. Now, this can be observed using current technology at a hyperspectral frequency of observation. what do I mean by that? Well, let's answer the question, what could the landscape look like using this modeling? Here's an apparatus on the left-hand side. Here are the technicians, and here's what they can see on the right-hand side. It gives us elemental interactions. It gives us the scope to see through various objects, subjects, and insight that we could not otherwise have seen. The cultural context of technology coming to Sri Lanka is thanks to Professor Christophe. He's currently visiting Sri Lanka, returning to the landscape after 40 years. He remembers how Belipola Arboretum was when he visited at the inception of the project. Pioneered several methods for 3D modeling, landscape topography, using specific technology and techniques for scanning the landscape. In my discussions with Professor Christophe, he believes that these technologies can assist landscape architecture and also help to design sustainable anthropogenic ecosystems. Dr. Ranil Senanayake, of course, has articulated the applied science of analog forestry, has inspired many field researchers from around the world to visit Sri Lanka. While a large body of data exists about analog forestry, the potential to study soil, water, and atmospheric benefits of the landscape at microspectral frequency could about Belipola Arboretum and the research center in itself. What is an analog forest? Well, like an ingrowth forest, the technology is to copy the natural forest structure in its architectural structure, as well as its ecological function. So just to break down the word analog forest, analogous to a forest, similar to a forest in original structure and function. Here's a little bit of a visual. Now, the applied science of analog forestry, it is concerned with what we call B2B ratios, improving B2B ratios. Now, B2B would be biomass and biodiversity. So you see how those two components come together in appropriate ecological spacing. And we call this a beautiful synergy, and we have visualized this concept over the last 30 years. I'm going to play you a quick video of what it would be like at the analog forest. And this is a kind of structure that was built, that was designed and planted no more than 40 years ago. So here's the video really fast. This is today at Belipola. So that was just a quick glimpse. Let me get my screen share back. Hold on. I'm just going to finish my presentation here, and then we'll let Professor Christophe continue. The current state of the environment surrounding Belipola it's quite prevalent across Sri Lanka and also around the world. Unregulated mining in this context has affected water tables, soil and nutrient retention. And it's a real problem. And this is just 200 meters from Belipola Arboretum, from that beautiful environment that you just saw. Because of the scale of this mining that is happening, the most promising jobs in the village are actually destroying, and it is lacking skill. It is lacking technological advancement, and it is definitely lacking considerations for biodiversity and biomass. As an education center at Belipola, we are focused to teach anyone at any level, actually, introductory, intermediate, or advanced levels of analog forestry, as well as practicing it. We practice habitat and biodiversity restoration. We promote research and development, bridging formal education through international universities, local universities, the National Apprentice and Industrial Training Association, as well as the Vocational Training Institute in Sri Lanka. And so today we are here to share with you this information that is brought to us via the international network and Professor Christophe. The vision is, together with the international networks, to inspire practitioners, researchers, the youth of Sri Lanka to enter these new areas of scientific inquiry, as well as integrate these technologies into your development of the future. With that, I welcome you back to life. Thank you again for joining us. And now, without further ado, I'm happy to introduce you to Professor Christophe. Thank you. Thank you, Professor. Go ahead.
Thank you, Dehan, for giving me the word. You should allow me to share screen so that I can do that. But first, I would like to say a word about the Belipola Arboretum and why I'm here. I was actually here 40 years ago in 1981, where I went to Belipola. It was a dry savanna grassland. I had met Ranil Sinanayak a couple of years before at the UC Davis in California. And, you know, it was very optimistic. I saw Ranil planting very small trees in the middle of the grass and hoping for the best. And I have to say, when I came back 40 years later and saw this piece of jungle full of animals, I was more than impressed. I was, in a way, relieved and convinced that, that what Belipola has developed with its methods in forestry could and should serve as an educational base for the future. We're currently in such a state of environmental fatalism in the world, and people tend to think that the end of the world is near, and they sort of lose the incentive to do anything. I think the Belipola Arboretum example, with its 40 years of existence, is a radiant example of how to fight environmental fatalism and to work towards the restoration of a natural environment, or at least the balancing of a natural environment in developing regions. I think that this said, and the reason why I'm going to give this talk today is because I've been working completely on the other end of the spectrum in high technology and in mapping techniques. And what I think could be very interesting right now with the results that have come through at the Belipola and the data, that we could actually bring in a sort of surveying system, three-dimensional Lidar surveying system to the site and probably other sites across Sri Lanka that would really help monitor and actually perfect this model of experimental forestry. I really believe in that very firmly. I think the ecological dogmas or theories of the 20th century are foregone. The theories were, we should conserve and preserve the natural environment as much as possible. I think we've passed into a new era today where we're going to be asked to design natural areas, not just preserve them, but actually design them. And that's a whole other can of worms, a whole other challenge that stands before us. So all this said, what I'm going to show, obviously, it doesn't have a direct relationship to the Belipola Arboretum, but the applications that you could derive from what I'm going to show you could really serve as a scientific basis for the research center that is now being developed. So I'm going to share my screen. Hopefully I'll find my... Yeah, I think we're good here. Is this good, Dehan?
Yes, yes, Professor, it's fine. Thank you.
Good. So what we have here is actually a point cloud model of the Alps that we've done, the Gotthard Pass. We've just cut a tiny little piece. It's a 50-kilometer long digital model of the entire Gotthard railway track and mountain track between Erstefeld and Bodio. So it's roughly 50 kilometers of mountain landscape, scanned through various methods. What I wanted to say, so that we can really give that as a sort of basis for this talk, most of the cartography done, or most of the mapping done in Europe, certainly in Switzerland today, is done with Lidar technology. Lidar technology was developed during the Apollo moon missions in the 1960s. Lidar means light radar, and it's a way of measuring objects, three-dimensional objects in space, and bringing back the information digitally into a computer in order to model it. So basically what you're seeing in this picture is not a photograph of a place. It is a still, it's a screenshot, but it is actually just one part of a very vast component of point clouds. And the way I want to explain point clouds today, that technology, LiDAR, which is broadly used in engineering and archaeology, should be used in landscape planning and architecture. It's only beginning now. But it's really a little bit as if you had minute, very, very small drops of dew, like rain, dew, very fine water, all over the surface of the ground, the earth, the trees, and that these drops get collected one by one and are actually referenced. So if we actually see, I don't know why I can't change my, oh, here we go. So landscape topology is actually represents an entirely different approach to the physical terrain modeling and design. This model allows researchers to monitor the deep scientific, physiological, biological, hydrological functions at a specific place in the environment through very precise geolocation. We've worked extensively. This is a laboratory that I share, the LVML at Zurich, with my colleague Adrien Guerre-Gamay. We've been working very, very intensely with the ecosystem service planners and hydrologists, and it really actually works quite convincingly. So the point cloud model as such is not my invention. It's a technique that's been available for the past 40 years in the research field. And it helps designers and researchers to grasp the landscape's complexity and character through different scales. So basically, I don't know why. Okay, that's fine. So basically, a point cloud is a field of pixels that instead of being flat on a screen, the pixels actually have a real physical distance between them. Each pixel is a point, so I've drawn them as a sphere. And the other thing is that each pixel has three basic geographic coordinates, X, Y, and Z, extremely precise, within the millimeter precision. Basically, the location of that pixel on Earth is determined. It's related back to satellites. It's a way of surveying the Earth with very, very high, much higher precision than the current GIS that has roughly a grid of 3 to 5 square meters per point. In the case of a point cloud model, we have thousands of points per square meter. A lot of people could say, well, what's the use of that? Well, the use of that is that you can actually develop these point clouds into a physical model that can then be used for a variety of simulation and also data bank. That is to say, in each pixel, in each position, you can accumulate, it's a little bit the Google model, you can accumulate pancakes, stacks of information on that particular pixel point, which then develops any kind of scientific research base. If you're a hydrologist, you want the meteorological information. If you're a botanist, then you get the information on the tree or the trunk circumference, or you name it, a photosynthetic functioning. If it's just purely a hydrological function like a dam or a bank, that pixel will have another level of information. And what Dehan was mentioning before, the evolution of contemporary hyperspectral photography, that is to say photography that is able to go beyond the visible spectrum, beyond the ultraviolet and lower into the infrared, gives a very broad range of physical, chemical, atmospheric informations that can also be fed into such models. So I'll start in 3 scales. I'll try and go slowly. This is an experiment that we've been doing with the Kyoto Institute of Technology for the last 6 years, almost 7 years. We basically brought in doctoral students, postdoctoral, doctoral students into Japan to train students on site. It's usually a 2-week workshop, 10 days, 2-week workshop. And the reason why I'm showing this is it shows how this technique is easily transmittable and teachable to young groups of students. And I think a lot of the young gamers today and the young people that are into 3-dimensional gaming and all that will feel very much at ease. This has nothing to do with gaming, or you could call it environmental gaming in a way. It's about really developing those skills very quickly. So the Ninigi Garden, the first garden we did, and here you see on the left, Matthias Vollmer with a little terrestrial laser scanner, a TLS, of the American brand Faro, and a student from KIT, I forget his name, is it Masahiro, scanning that garden. I believe I asked Matthias in this very small rock garden at the back of a row house in Kyoto, in the middle of Kyoto, I think there were at least 30 or 40 scan positions done to get a very dense, complete model of that physical realm. This, in a way, is a section. It's just a still on the model that we have. This is the digital model that we have. And what you see in that section, and it's not drawn, it's actually as if you took a knife and cut through an electronic cake of points. We cut through the house that we've scanned inside out, this old traditional house in Kyoto. We see the engawa, the sort of platform that is outside the door, and then how the terrain, the garden with its rocks and stones and steps, the very irregular ground of the garden, how that unfurls. This is all measured by light, by these terrestrial laser scanners. And of course, with a group of 50 students for a week in this house, we managed to get the building extremely well scanned. This is just a view of the model where, in a way, and that's what's the magic, but also the disturbing aspect of point cloud models, is you see through them. Even if the wood is opaque, you see through them because of the nature of the system. You have, remember, it's a cloud of points with black in between. A point is information, black is no information. And this information is geographically positioned, 3-dimensionally spaced. That's to say the pixels that are red that show the wood are definitely in front of the garden. They have their absolute position, but they allow you at the same time to see through. So this is the sort of technique that was developed. I'm just showing you again the bottom. You may find that interesting. That is a section through the whole model. It takes the house from the street all the way to the back garden. And this is a plan view of the scan that we did. Plan view simply made by removing the roof. We scanned all the way to roof. We removed the roof and we just show the entire floor. We never, as a matter of fact, work in plan when we work with point clouds, but we can produce plans. Like in this case, we produced a plan, but no student ever really worked in plan. They worked in model, in space, in 3D. And I think that's the conceptual revolution for all of us in research and design teaching, is how do we teach three-dimensional thinking? Even though we do evolve in the three-dimensional world, we seem to have been trained in the last 50 years through mapping and planning methods that tend to reduce things or flatten things to a flat piece of paper colored by numbers. That cannot be the correct way to go. We need to be much more in the physical realm. So that's what we teach with these students. This is an example, and it's really true, of what students do within a week, within 10 days with a student. This is a little film that they made. It's just one amongst many, where we're going to go from the street through the Ninigi house into the back garden. It also has geolocated sound within it. This is a student project, a 2-week project. And here we're simply moving the camera in the model through the house towards the back of the garden. You hear all the wood sounds and tatami sounds. The other nice thing about point cloud models is you can walk through walls without hurting your head. You just go through the membranes. Here we're going into the kitchen before getting to the garden. Now into the garden. So as you can see, the great detail in the foliage, in the vegetation, in the rocks. Each tree and plant is positioned, can be inventoried, geolocated, measured, monitored over years, the whole thing. This is actually a house owned by the Kyoto Institute of Technology. It's a student house, and we can definitely go back and monitor it over time. Now we're just going out again, back the way we came, much quicker into the street. And so what's incredible with this technique is the young students, the young kids, are able to navigate in this stuff very, very comfortably, very, very quickly, much faster than me. I'm incapable of manipulating this technology. But what I find very interesting is that it actually works and can be taught quickly and be transmitted. There's another example, very classical gardens. I won't spend too much time on that, where we geolocate sound and we also record the garden in point cloud. This is a view of that temple room, open to the garden with the azalea bushes trimmed in the back. This is again just a screenshot of that model. Here we see the students learning how to use handheld devices with this technique, very simple. And again, you see the section, you see the photographs on top and the section of the entire scanned garden. I mean, the house we saw is hidden behind these trees here. And this is again a plan view, which is just the result of the point cloud model scanned. This is the temple where we all took this view, the azaleas here. And we're going to have a tiny film showing the shishiodoshi here in this corner. So the shishiodoshi is a water device used to scare away the wild pigs that destroy the plants. It's a bamboo tube that knocks every 30 seconds or every minute. You're going to hear it. And here we're just zooming into a corner of the model. Now, of course, this model could be scanned much further in detail. You could literally have every single leaf on every single bush all around. I have colleagues like Matthias Vonder working on the underground now. The root world will certainly come to be mapped within 10 years from now. We're not there yet, but this is all going to happen rather quickly. And I think that working on such geographically positioned models is the way of the future for a place like Belipola. I could very easily see corners of Belipola being developed and scanned very intensely and developed into a working model. This is the Midera Garden. So I'm just showing this series of Japan, not all of them. This is the last one I'm showing. These gardens. What I like about these examples is that they show a very small scale, very precise, but of course this scale can be deployed at a variety of other scales. That's to say the precision could be developed much further. Midera, this is again a section through the house. We took the roof off. This is the deck where you saw the people standing by the pond, and we just models much bigger. Here we have the Kyoto Institute of Technology students learning the sound methods. This is Nadine Schutz, the sound specialist. She did a whole doctorate on acoustic landscapes. And here they are recording in the garden, interviewing fish. And this film, it's a very simple film. It's just a slow panning in to the back of the pond here. You're going to see how the geolocated sound really works admirably. This is also a video done by Nadine Schutz for her dissertation. Look at the detail of the branches of the trees. I mean, everything, of course, it's a still, it's not alive. The branches are not moving in the wind, but it is really a framework of geographically positioned points that allow you to calculate the surface area of foliage, the cubature of foliage, of course, the cubature of ground, the topography, existing topography on the ground. All these applications, I'll show that in a minute, you can basically integrate within the framework of this method. Here we're just moving very slowly, a bit like a butterfly or gliding through that minute landscape. And again, this is a section through that same garden. So that's the big half of that digital point cloud model of Midera. It's actually a site that is not open to tourists. It's a private shrine belonging to the Zen Buddhist monks of Kyoto. You're privileged enough to go there for 2 days to scan. This is 2 days of scanning. It just shows the result from the output. Extremely precise output for architects, archaeologists, and even ecologists. So if we were to look at hyperspectral information in a model like this, then each tree species would give out a different frequency, depending on its rate of photosynthesis, et cetera, et cetera, et cetera. So you can literally monitor through this model successively over time, like once a month, once a week, once a day, use different parts, for instance, of the Belipola Arboretum to develop areas of research further. Here we are recording fish. This is again a beautiful view of that model, point cloud model of Madeira, the garden. More pragmatic, more down to earth, how it's used in practice. I mean, I have an office practice in Zurich, a small practice, and I work often with architects, and often the whole question of topography is incredibly complicated. You get bad data. This is a site in Brissago on the Lago Maggiore. This is typically what you would see in a sort of luxury suburban development along this lake. We had very bad contour information. It was old terraces, at least 200-year-old, that were not clearly mapped. We didn't know exactly what the height of the building was going to be, the new project. And so here I came in with a team of scanners. We scanned this site. And from the scanning of the site, this is your typical sort of Riviera development. As you can tell, all the buildings are following the contour lines, obviously. It's a very, very steep slope. But what you can do with this method, once you scan your site, your project site, you can really go in to develop different tools. This is an elevation of the scanning we did for the site. So it could be even a parcel here or in Bergala for that matter. It allows you to go back to the geographic information. So for instance, every contour line that you generate in this plan, these are meter lines, can be positioned. That is to say, you can develop 50 sections along the line before you build your project to really understand where are the older terraces. Here you see the sort of deformation of old terraces with half crumbling walls. So this is an information that we get from the point cloud model. You're able to go down the z-axis of the point to the ground, and you get incredibly precise ground information. And it allows you then to really work in this way. So the way it works with point clouds is in this famous z-axis, you can filter to the lowest z point, to the z point that is most at the bottom of the column, which allows you to filter. So if you see this site, which looks like a complete suburban mess, you can filter. You can go like this. So I go back. This is again the same site. And here again, you filter. You filter by going back on your point cloud model to the lowest Z referential in your 3D model. And that gives you an incredibly powerful tool to read existing topography. And it allows you then to make the right decisions in terms of preserving historic terraces or adapting them, inserting the architecture within that particular condition or not, or ignoring it. And this is the architect's project. This is Sacha Men's project that you see on the upper right, this sort of black box, sort of on stilts, landed on the field. And what you see here, those are the black boxes. You can embed an architectural project, a ready-made 3D model within the point cloud model. There's no mesh problem as we used to have in the GIS mesh system. Here with the point cloud, it's like a pincushion. You put in your buildings and they land very precisely topographically within the model. So this is, again, more of the play that we have. We can also go back to, this is a very old Swiss topo model of Lago Maggiore, Brissago. This is the biggest lake in Italy, at the border of Switzerland. And what you see here is our site with our point clouds. And this point cloud model is embedded in a much bigger GIS. You see the triangular grid for the lake here, a much bigger sort of GIS triangular grid. As I said earlier on, the entire Swiss territory today is scanned in point cloud Lidar. The city of Zurich, I'll show that a little bit later, is served as a point cloud model. I mean, in a way, this technology is going to become ubiquitous and is going to be served throughout the world, because Lidar is the technology that people use today to map. Leica and Regal have developed these tools that are now worldwide spread. And I think it's really important to understand how, with history, how we evolve our methods according to techniques. I mean, we see that in the past with the development of the theodolite in the 19th century. These surveying and measuring devices influence very strongly the way we work or don't work correctly within a given environment. So just to show the power of this project, it's a rather exceptional project that we did with an NGO called EcoPeace that works on, well, at least tried to work for a long time, trying to maintain dialogue between Jordan and Israel, particularly at the border. As we all know, this has not followed its fate as planned, but we had the privilege with a team of researchers of the ETH and some researchers from the Technion in Haifa to go over the border into Jordan and to use this point cloud technology to map the site of the Nahayarin power station, which was built under British mandate in the 20s and early 30s. What it's showing here is how within 2 days we're able to deploy the technology to scan a vast area of territory. So this is a picture of the site in the 1930s. The entire waters of the Jordan and the Yarmouk were dammed, created a big lake, and it provided 80% of the electricity for the whole of Palestine and Transjordan, as well as providing abundant agricultural water for the entire Jordan Valley down to the Dead Sea. This is the construction of the project in the 30s with all the very proud workers of the region. This is the amount of water there was at the time, which no longer exists. Both the Israelis, the Syrians, and the Jordanians have taken all the water out of this valley, which is a huge problem. And these are the ruins from the 1948 War of Independence of Israel, where this ruin that stands on Jordanian territory with these Washingtonia palms in the background, this ruin of a power station. So you can say, well, what's the point of coming to the ruin of a power station? Well, it was actually very useful. If you look at this device, this is a TLS, a terrestrial laser scanner, that has a range. In a way, a terrestrial laser scanner works a bit like an onion flower or a sphere. It has a range of 1.5 kilometers. That is to say, if you look at it as a flat disk, it has a range of 3 kilometers, right, overall, in the overall diameter. But you actually have a scanner that is precise within 3 millimeters in the z-axis at 1.5 kilometers. So this device was able to scan vast areas, and we chose different hills on the Jordanian side. We were only in Jordanian territory 1 day. And by doing this, here we're on the Israeli side doing the other thing. So we use these different heights. This is the Golan in the back. We're behind the Galilee mountains. And finally, what you get as a result, and probably doesn't look very impressive, this is where the power point is, the power plant is here. This is the Jordan Valley, Jordan River Valley. And what's amazing is we managed to get a whole site model without ever walking. This is heavily landmined. It's been closed for 70 years, this border. Landmined, you get a couple of wild boars that explode every now and then in the valley. A very dangerous area to go. But we were able to scan that whole area and actually even to have you travel up the Jordan River. Here you see in the foreground the Ottoman Bridge, railway bridge from the Hajj railway line that linked Haifa to Damascus at the time. You see the old Roman bridge in the back. This is the Gesher and the old Mamluk fort here. The only thing we're going to do is we're going to go up our model. This is our model. Here you see the mountains of Galilee in the back a bit. That's how far or what range we had with our device, this Regal. And what we're going to do is we're going to fly for the first time. We're going to travel for the first time up the Jordan River. Nobody's done that in the last 70 years. And this is what I call a sectional flight through the model. Going up the Holy Jordan River. Look at the level of detail. I mean, you can literally count every blade of grass in this model. You can locate every bush, every tree. I mean, look at the amount of information you're able to retrieve within just 2 days of campaigning, not even going in that riverbed. We didn't go there. It was just scanned from different positions, and the scan sets merged and created this unitary riverbed that we're now enjoying. So I think that that's the reason why I'm showing this project. Of course, with all the other issues linked to that border, I mean, of course, we could go into what would be the appropriate ecological project for such a site, such an extraordinary site. My first comment would be, first of all, please bring back the water, which is no longer the case, but I'm not going to go into geopolitics right now. We can address that later. This is the inside of the power plant. This was scanned by the Israeli team from the Technion in Haifa, Professor Sagi Filin on the right. This is the scan they did with a close range point cloud scanner. And the reason why I'm showing that is you do a specific object or a specific place in the model, you scan it, and you embed those point clouds that have a higher density, of course, within the much broader model. So in a way, what you see here is a highly scanned object placed into a less densely scanned system. You remember the position of the scanner. We had it on the corner of that plant. That's where you get these laser shadows. You know, any object that stands in the way of the scanner creates this huge shadow, right? You see it radiating across. You see also here the radiating shadows. That's how it works. It's a light radar. If there's an object blocking, you can't see behind it. And this is, again, part of the model. I just think it's an interesting thing to look at because it really shows you, I mean, this looks like nothing. It's just like green porridge, right? But as you move in, you realize that it's really topologically representing the crust of the Earth, the entire crust of the Earth. This is where 3 tectonic plates meet, 3 continents, Africa, Asia, and Europe. You know, it's very heavy. And look at the level of precision that you have in this model. This is a 3-dimensional model of the whole site. So these are pictures of how it was when there was water. I'm not going to go into this history. The reason is that I'm showing you sort of a gadget or a trick. This bridge, this steel bridge that was designed by German engineers for the Ottomans at the end of the 19th century, got knocked out when there was the war, the Liberation War. This is where the bridge was. It's no longer there. It's actually here in the river. It's lying on the floor. And my postdoc researcher, Philippe Ulrich, just had fun and fished the bridge out and put it back on. That's what he did. He took the model of the bridge and put it back on. So it's just showing how you can actually operate within a point cloud model, both working on recording history, recording the site, modeling transformations. You can move objects like this bridge, you can move it, but you can also monitor each plant that is geolocated, can then become referenced and become a further object of study over time. So it's an extremely powerful information system that you have at your disposal, much stronger than a zoning plan. We found some technical drawings just to demonstrate the level of precision. For those of you that doubt the precision, here Philippe Ulrich did a film of the sort of water intake line, the canal intake that took the water from the lake into the power station. So what you were following here is the line of the intake. That's the lower line that you see drawn here. We're just going through the model. It's again a section through the model. And the reason why I'm showing this is that you're going to see this, this technical drawing that I just showed you before. We embedded the technical plan on the model, and it matches almost at the millimeter the scans of the building that we did. And I think that's what's interesting, is in a way, with the point cloud technology, you're able, of course, to bring in meta information, metadata, and you can actually literally use physical three-dimensional techniques, engineering drawings. Here's a drawing being embedded. So we embedded the drawing in the model. We have a half section, and there you're simply going to see half of the power plant. This is the core of the power plant right here. Oops, sorry, didn't show you the whole thing, but you got the gist of it. We also worked in Singapore recently on the urban heat island problem. I think that urban physics, but also rural physics, I was discussing this question with Randil Sinanayake last week. I honestly think that, for instance, understanding the physics, microclimatic physics of a hedgerow or a forest edge could be an absolutely fantastic source of information and of development in the coming years. So what we did here, and the reason I'm showing you this is, again, the scale of the territory that we're showing. This is work on the old Malay train line that runs into the CBD in Singapore. This is the island of Singapore here. And we only took the line from the high point, Bukit Timah forest, with this idea that we could maybe convey cold air from the forest down into the city center. So it was a very naive premise of saying, we're going to bring the cool air of the forest down to the hot spot of the city. As you all know, under the tropical and equatorial climate, convection and air movement and temperatures don't work the same way that they do in temperate zones. It's a whole field of area itself. These are heat maps that we did in point cloud. We managed to get, finally, after a year and a half of negotiation with the Singaporean authorities, to get a piece of their point cloud model, because of course they have the whole island scanned in Lidar, like Switzerland. We got that. And we also had the researcher, Philippe Bush, scan the top of buildings. And what you get as a result is quite an extraordinary model where you have this green rail line moving through a hyper-urban setting, but somehow this green line, I said, a model where, working with Jan Carmele, who actually is our professor specialist in urban physics, he explains how the relationship between tall tower buildings and cool forests works, because you get what you call not only the albedo, but you actually get what you call buoyancy, which the buildings convey air movement towards the roofs, and the temperature differential between the top of the roof and the cool forest next door starts activating wind currents. I mean, ironically said, and I have to say it very clearly from the scientific evidence we got doing this research, is that in order for air to move in the forested areas of Singapore, you need buildings to create that movement. That's the irony. Here's a journey through this very long model. I think we're dealing with a model that's roughly 8 or 10 kilometers long. And again, you know, the reason why I think it's important to show you this is this is a scan of existing trees along an existing train line within an existing neighborhood of Singapore. We're leaving the Bukit Timah area, and we're going to slowly glide down on a 6% slope, glide down to the harbor area of the central business district. So here we're sort of shooting down the way. Each tree, again, can be georeferenced. Each tree can be scanned much more than it is. They were all scanned from the top of the buildings. We embedded these color scans that we did in the bigger LiDAR model of the city of Singapore. That's why all the rest looks gray. And it's, as I've told you, geographically informed three-dimensional modeling. And all this is the same technique. What you can do with that is actually, and I'll show you the designs that the students did, we always based our learning curve on either short workshops, like the ones that I showed you in Japan, or a semester long, like a 15-week, 3-month session where they really learn how to work on these unwieldy models. I mean, here we're talking about easily, 100 million points of information, if not more, how they actually work within that realm and embed design and make correct design decisions within that world. I'm going to show a couple of series of that to show how we use the physical model to experiment with physical change and physical phenomena. So here we're heading slowly towards the CBD. We're arriving. You can see it in the background with all the cranes of the harbor. So we're almost done with our 8-kilometer journey. It's all one model, right? This is what we hold. And of course, we had our students work on we divided this very long stretch into 3 sectors because we work down to the 100 scale, you know, when we go into design. But the technique and all the pseudos and all the teaching that I've been doing in the last 15 years now at Zurich has been based exclusively on this technology. So we did workshops with master students from a school called SUTV in Singapore. Here you see the session with the students. It worked very well. And these are some of the designs developed by the students within a point cloud model, where they literally plant a park with water bodies and try to develop alternative solutions to urban development. So here's the Bukitima, and here's our cooling spot here, where we say, please put the buildings on the edge and allow these southwesterly winds to come through and irrigate the place. This is again the same site that you see here with just point cloud modeling. We also worked in Jakarta in the sort of environmental black hole of Indonesia using point cloud modeling techniques. Here we picked one of the 13 rivers of Jakarta, the Ciliwung, which runs by the presidential palace. The reason why we chose that river is it's an absolute basic case study in environmental neglect. The river is 100 kilometers long. As you know, Jakarta hosts more than 30 million, 30, population, as much as Sao Paulo. There's no water management, there's no water treatment, there's no water supply. I mean, it's really a very paradoxical environment. We use this technique in Kampung Melayu, where they regularly get flooded in the center of town under 8 meters of mud and crud each year. This is the sort of slum settlements along the Ciliwung River. The buildings are built on what we call plastic lasagna. Plastic lasagna is a new geological phenomenon that's about 40 years old. And we did some core excavation. There is you get plastic lasagna going down almost 10 meters deep into the riverbed. It has a direct impact on vegetation and on health, as you can tell. The other important thing that we heard is that the Ciliwung water, the original headwaters, I think that we can account for less than 10%. It's probably about 5% of the river is the original headwater. The rest is all industrial and domestic effluent, no treatment. So this is the point cloud model we managed to do of central Jakarta. It doesn't look like much. It was very complicated to get this point cloud model done. But this is the basis we finally got after 3 years working in future cities, using a variety of scanning devices and trying to move through this complicated environment. And we worked with hydrologists, with ecologists, foresters, architects, landscape architects, sociologists, testing a variety of phenomena along this idea. And what we really developed was this idea of a lineal park, a green park. You could call it a hedgerow system within the city that would connect the heart of Jakarta with the hinterlands. Here you see a system with step bridges, very attractive project, but actually completely disastrous on the level of flooding. This is the project itself. Also in models, these are 3-dimensional models of the project. This is another one with a variation, sort of park clumps on one side and the other. All I'm showing here is this point cloud basis serves as a topographic reference to develop design. These are architecture students, of course, developing their architecture and landscape. Papayas growing there. this idea of a very productive landscape. Here you see a more idealist group using the traditional stilt house urbanism in the middle of the river. I don't know how realistic that is, but this sort of idyllic vision of going back to a river of the origins was part of the brief. You know, we accepted these approaches. I think this is probably the most interesting part for all of you, is that we took each student project through parametrics. Within a point cloud model or within a 3D model, you are able to simulate flood events. And what we did is we simulated flood events through a variety of projects, and some projects were quite successful and others were absolutely disastrous. The result line is the major flood, the last line with all the red indicated things. You see the top project, the top two projects are going completely out of whack and are flooding the whole neighborhood, whereas the one below, the lowest most, is the one retaining the most efficiency in terms of water management and flood management. What I find interesting with this technique is the professor is not only making a value judgment or sentimental judgment on the project, the point cloud modeling forces the designer to go into physical verification, simulation. I'll show other examples of that. This was the whole team. We have students from Singapore, from the University of Indonesia, and from the ETH, Zurich, from Switzerland, all mixing together and working on this very exciting project. That was about 7 or 8 years ago. As you've seen in the beginning, we've scanned mountains, we've scanned very big ranges. So what's really interesting with this technique is what I call the transscalar capacity. You know, classically, planners were trained at 1 to 5,000, 1 to 10,000. Architects were trained at 1 to 500, 1 to 200. And, you know, somehow these different scales meant different worlds, different realities, and they didn't really interconnect. What's interesting with this very big scale Gotthard model that we've done, that we're going to exhibit again next year at the ETH, is that you're able to manage these different scales simultaneously. You can focus on the house in the background, but you can also focus on the whole mountain range. We developed a variety of tools. This is a Swiss drone from the early year 2000, swinglet, would self-fly back. A very nice tool, not very precise in the Lidar, very vulnerable to birds of prey and attacks by eagles. But we were really trying to develop tools that allowed us to scan both from the ground and from above. And this, of course, with the evolution of drones in the last 20 years, has become more than doable, right? We use mobile LiDAR, you know, LiDARs that you mount on vehicles and drive down roads, which allows you to scan entire corridors. And of course, site-specific actions with team members using the device. These are some of our first scans. I always thought these scans were very beautiful, looked like a 19th century aquatint. Basically, all it is, it's information, no information. You know, a white dot and a pure LiDAR scan is just a white dot on a black background, but that is done then physically or spatially positioned relative to other branches. No branches overlap, no branches cross here. They actually each have their distance. And that's the model of the Gotthard, this 50-kilometer model that I talked to you about, going from Erstfeld to Bodio, where you see a whole mix of different LiDAR types. We're not trying to represent it. I'm just showing this as a data set. And here, I think we're at roughly the 1 billion points of information mark. Of course, it poses question of how you store that and how you manage that. Working on point cloud models of this size with programs like Unity allow you to selectively work on just an area and just call the points of that area to the foreground. You don't have to wield the whole model each time you're operating, depending on the scale you're at. This is an example of a science exhibition that we have at the ETH each year, where visitors are able to go into the model with these strange goggles and able to walk through the Alps at their leisure. This is the tremolo. This lady is moving in. So in a way, what you see in this demonstration is it's not a perfectly made film with a soundtrack. Here, the person has a headset on and just walks into the model, you know, and can wander around. And really quite extraordinary technology, I have to say. This is again by Matthias Vollmer and Johannes Rebsamen. I asked them to do a very specific model of the Gotthard. Here you see the Tremolo Road winding down on one side, on the left, the old Tremolo Road, and the new Tremolo Road on the right with the tunnel. I asked them to do a section through the mountain range so you can see the underground. You see those white lines that are on the upper right, left-hand corner. Those are the underground motorway tunnels and the high-speed tunnel, the NEAT tunnel, which we got from the Alps Transit in the back. And I asked Matthias to cut a section through the mountain so that I'm explaining to you that our model is three-dimensional. I mean, we're showing the mountain not as a picture, but actually as a physical shape. And you have below the ground, a couple of kilometers below ground, the tunnels that are going through. And this is only a beginning. I mean, we're mapping underground in a variety of ways thereon. So much for these sections in Göttingen. This is, again, a demonstration. This is where a lot of infrastructure comes in. And here I just asked my team, please cut through the cake again, cut through this model and show us how that thing works. Because it's hard to understand if you don't really cut through it. This is the Reuss River below, and you're able to cut through the entire infrastructure network and village, in a way, of Göttingen, showing how infrastructure relates to the environment, how it comes into contact. Of course, for questions of water management, etc., it's very, very important. We've also been fascinated and horrified at the same time by the loss of snow and ice in Switzerland. The glaciers are melting very quickly. Here you see a few students wandering around on the Morteratsch Glacier. And we did a whole 3 series until these big boulders came tumbling down right next to us. We worked 3 years in a row on this glacier and documented it, and actually did even an exhibition of that, where we scanned the sound of the glacier moving and the physics. So here we have the students explaining what they did. This is our workshop. Here you see the microphones. Some of the microphones were frozen into the glacier overnight and then recorded. And I'm going to play now the sequence. This is the face of the glacier with our student group in the front. This is not a mountain, this is ice that you see, the quickly vanishing ice. So here we go. All in point cloud modeling. Of course, monitoring ice melt is one of the major tasks of this technology. Here we're just doing ambient sound measurement at the same time. This is all on-site recording. the croaking sound of melting ice. Yes, so that's a big theme for us right now. We've also worked on the dam system using the same technique, scanning all the hydroelectric project, the capturing of water. Here's a dam on the top. And again, these are point cloud scans of the valley, where you see the extraordinary precision that you have in documenting absolutely every element along the way. This is all natural sound, right? As you can tell, water is a reflective surface, and therefore it doesn't register on the Lidar. That's the one big drawback about this technology, is it can scan everything except water, which just diffracts, doesn't send back the information. This is a project that I started 20 years ago in my office. It's an artificial mountain based on tunnel rubble from tunnel building with the Alps Transit company. And this is where we asked the engineering company, the tunnel company, to do the first Lidar scan of the site where they were going to make the mountain. So we worked. It was just at the beginning of the construction. We worked with a base made out of point clouds, which gave us extremely precise terrain information. Every rock, every crack, every tree, I mean, everything was extremely precisely done. Of course, this is embedded in a geographic mesh, which is much less precise than what you see here in the foreground. We're talking about 3.5 million cubic meters of tunnel material, so it's about 7 million. Usually ground or exploded, with huge problems with nitrates. The reason why they couldn't put the mountain in the valley is it would heave up the motorway and the river. It would be too heavy. It would deform the terrain. So we had to put the mountain, on a rock side, in order for the pressure of those 3.5 million cubic meters not to exert too much force. We also used urban compost to activate the skin, the outside of this artificial mountain. This is the technique being developed. You see the contact between this mound and the original rocky mountain of the Sottocenere. These are the edges of that construction being completed. This is Ilmar in the foreground on the left. He's definitely the topographer working with me. And here you see a section using the point cloud model, a section of that mountain, which goes up 150 meters and in a way butters the material on the slope of the mountain. Sorry. This is what it looks like in construction. A very big piece of artificial material. The material, which is ground gneiss, because it has been changed into meal, actually has a highly alkaline reaction, which means the vegetation there, most of the vegetation in Ticino is on granitic and crystalline rock, highly acidic, and this is an alkaline island in a way, being placed in the middle of nature. And the Holocene technique, where we use the local seeds within that 50 centimeter skin of the hill, and where we ended up generating flower meadows out of this engineering piece of work. So that was quite a success, stabilizing 3.5 million cubic meters of material. That too is part of the point cloud technology. So what I'm saying is you get a very broad range of things. I've always told Renil, it's both a topographic tool that allows you to define new topographies, but also to monitor, of course, biotic life upon it. This is a model of the city of Zurich that I talked to you about. So currently, the city, I mean, all Swiss cities now are available, are open source as a three-dimensional Lidar model. They just fly over the city once a year or once every 2 years, and you get a three-dimensional model of the city. This is Zurich Lake, the waterfront, and we're going to go into the Schanzengraben. We're in the same model. What I'm trying to show here is we're within the same model. We're coming into the city of Zurich, and we're going to come into this old defense line. It's the old Baroque city sort of moat defense line, and we're going to go all the way down into this model. So on the side, it's the gray model. It's a bit like what I saw in Singapore. This is the Lidar provided by an airplane, where you get all the city objects inventoried. And we came in with our own devices along that specific waterline, which much higher resolution and color. So you get a mix of color and black and white in this model, which makes it interesting to look at. And we are evolving through this model. We're moving into the model up to the Old Botanical Garden, which this is again a film done by Matthias Vollmer, who's working a lot on Zurich right now, on the Zurich Underground. And he developed this extraordinary model. We're arriving slowly but surely at our botanical garden here. But again, this level of detail was done because we chose to scan all along this canal. Students helped us do that. And it's really a question of where you want to focus your attention. The model is there, the framework is there, and you can really pick your pool of concentration and specialization. Be it vegetation matters or construction matters. It's all the same, since character identification is not a given. In a point cloud model, you set up the identification procedure, right? How do you differentiate between a tree and a wall and an object? So here we have defense walls, and you're going to see on the right-hand side, there's a 200-year-old defense line underground. You're seeing here in transparency through the wall, the casemate, the sort of soldier's reduit that is below ground, hidden in the wall. We're going to take you into that casemate because we scan the inside of that place too. So you're in, there you go. All within that big city model I showed you at the beginning with the lake, right? We're all within this model. And now we're going to go above ground. We're going to start trying to climb up, get to the garden, up the stairs, and into the conservatory, into the greenhouse conservatory. And here you're going to see a delightful Swiss detail where Matthias Vollmer focuses on a handheld device to activate the windows in the end. I mean, the reason why we're showing you this is it shows you how we're going through different scales, and we're able to actually operate each time with very high precision at each one of these scales, and they're interrelated. This is the mechanism that opens the window, done, of course, photogrammetrically, but embedded in our city model. You know, so it's really a demonstration of technique that I'm doing here today. What you do as a researcher, and these are some of the quickly shown sections through the city. That's where we were. We were underground here. This is where the handle was. And now, of course, the robotic landscapes. I mean, when I started doing this work, there's a very big NCCR-funded project in ETH. It's one of the biggest research projects in Switzerland right now on robotics. And when I was approached to help colleagues from Cola out with robotics, I was very allergic. I mean, my first reaction was, I don't want to have anything to do with robotics, you know. But lo and behold, after 3 years, you'll see the results. There is something to be said. The other irony with that is the robotic world uses essentially point clouds. The self-driven car, for instance, self-driving car uses a Velodyne puck, Lidar puck, which gives out on a very regular basis information about the space around the car. So this Lidar technology is becoming very, very widespread, both in industry and in the current world today. So we did a series of 3 studios. I'll just show two examples of that. Of course, this is the Menzimuk developed by Professor Marco Hutter. Professor Hutter has already developed some rovers for NASA, for the Mars expedition. His rovers are up there. He's also developed rovers to work in nuclear plants, non-driven rovers. And this machine, the Menzimuk, is operating without a driver. It's a self-driven device that can be used for emergency rescue work in flooded areas, et cetera, et cetera. It's really a nascent technology, and we firmly believe that this robotic technology will serve the environment in the very near future. I'll explain. So here are our students getting trained in this milling and modeling device. Going on site, here is Bondo. Bondo is dealing with debris flow. We chose the theme of debris flow rather than flood, because debris flow is a big threat today with the permafrost melting in the Alps. Debris flow is when rocks collapse down and behave like water in a riverbed. You'll see examples of that. Very violent events, and how to deal with that, including robotic technology. So this is one of the examples. The peak Cingalo collapsed 4 years ago in Ticino, killing 11 people and creating a huge debris flow, sort of shooting into the valley through the village of Bondo. This is all linked, of course, to climate change. What we did is we actually used the material, and the idea was to redesign the material of this riverbed is in a manner to accept future events and actually allow for more sediment distribution across the field. Here are the different flooding mechanisms. This was the second studio that we're developing. And the idea was that these robots would come in and rearrange the bed of the river. So this was the sort of final studio that we did, the case of the River Guerbe behind Bern. The Guerbe is a classical case of debris flow river. It has 120 concrete steps built since the 19th century, whether it was wood steps and then stone steps and then concrete steps, all the way up to prevent catastrophes to happen in the neighboring villages. The concrete has not worked so far. It breaks. When you see the events, you realize that they actually explain a lot of things. Here are the steps being built. And our approach was to say, let's get rid of all the steps and let's deal with the debris flow phenomenon the way it is. How can we deal with it and manage it ecologically using the robotic technique at hand? So we would have literally robot. This is the example of a debris flow in Vallis, just to show you what we're talking about. This is where big rocks behave like water. Very dangerous. Very dangerous indeed. Over the step. So what we used was this simulation technique. We worked with an institute in Switzerland called the VSL that developed software to simulate debris flow in models. And we gave that to the students. And what was really interesting there is the design wasn't just me, myself, I'd like to do this. It was about iteration. You tested shapes and ways of forming the ground without the steps, just forming the earth and the rubble in order to control the flow. What you see in this demonstration, on top, completely disastrous, and at the bottom, very well contained. But as I say, by tweaking the topography, we were able to develop a model, the sort of herringbone model you see in the lower right, showing how we were able to control that flow. And that for the student was a revolution. They were able to test, run, and really for hydraulic engineers and students, it's really quite a revolution. The result is of course, this sort of completely open landscape, just with mounds and this sort of herringbone arrangement that contains on this alluvial pan the basic shape and the basic effects of that debris flow. We've worked on urban studios. This is a scan done of Zurich, done by Dennis Häusler. Our studio was on the left, right-hand side of this model. And here again, you see how the model of this stretch of river in Zurich is used. Each tree, each object can be accounted for. This is again a sectional move through the model. And we teach basically our students to work with this means through and through. There are the methods. We have the method down now. And there are studios. And here are some of the design results. I won't go into the details of that. Again, another studio that we did was the Magadino plain, where you were working in a delta area, flood-prone delta area, again on a point cloud model base, asking students to develop as elegantly as possible sort of design solutions to control this surge of water in that area. I think that I will conclude on this theme, just basically to say, this is again the Magadino plain. It's basically the Ticino River arriving in the Lago Maggiore. The Brissago site that I showed you before was on that far side. Here you see the point cloud model, very precise information. In a way, what this plan is showing is that nothing is above 1 or 2 meters in height elevation relative to the lake. So we're dealing with very, very flat terrain. And you get this understanding of topography and how vegetation, plantation and management can actually be arranged for a better future in the regions. These are the publications, a few of them that we've done at the chair, the pamphlet series, of course, the big books, Course of Landscape Architecture, Melting Landscapes. We've got a lot of prizes. This was work done by students and researchers on melting ice in the Swiss context. I thank you all for your attention, and I'm open for questions now.
Thank you so much, Professor. That was very engaging. We will keep this panel and this discussion open for questions now. There were some questions typed in the chat window. If anyone wants to unmute themselves, I see Ranil has his hand up, so please go ahead, Ranil, unmute yourself.
Okay. Christophe, thank you very much for your presentation. I think it was very, very elucidating for all of us. 2 questions I have for you. One is, can we model airflow through buildings? Because Colombo is coming up with no regard at all for the airflow that has to flow through the city in order to keep the air quality. And the air quality is getting disastrous. So first question is, can we model airflow through the system? The second question is, we have now almost 5 feet of sea level rise before us. And a lot of our agricultural rice producing lands are going to get salinated. Is there any way to model this and look at the areas that are going to be salinated in the future so that we can take some action about it? So air and water. Thank you.
Okay. Thank you for your questions, Renil. I mean, the answer in both cases, of course, yes. I mean, we have a colleague at ETH working on what we call urban physics, Professor Jan Carmile, who actually has noticed that in cities, because of the effects of buildings and also the effects of vegetation, the wind, even if you have a dominant wind blowing west to east, the air currents in the city are very different. They don't follow the dominant wind. They actually have contrary actions and turbulence. And this is modeled. You can actually model that and simulate. What you do is you set a wind speed and you take it through. So the more classical models use styrofoam buildings, put in big aquariums and using water as the fluid vehicle, but now you're able to use the point cloud model to develop that. And the urban physics is going to become a critical science because in a way, in the domain of climate research, we're all working at the planisphere, at the sort of planispheric scale, but we're not really working at the local urban scale. That is to say, the parameters and the whole algorithms change as soon as you change scale, you change method, and what you see is much more diverse microclimatic things. So yes, the answer is we're going to be developing, we're developing that right now at Zurich, much more research in urban physics. And I think one thing that would be really interesting to launch in Belipola is what you call rural physics or hedgerow-physics, which could really revolutionize also the science of environmental planning and management in rural areas of the world. So yes, this is the first field that's developing. The second one, as you can see, in terms of topography, I could have shown other examples of projects we did in Sardinia, in the salt flats. Because of the incredible precision that we have, we're able, we worked in Dordrecht in the Netherlands on the Rhine flooding. I didn't want to show everything we've done, but we've been developing that technique. We're able to determine very, very precisely levels. If you're going to protect areas, if you're going to, I imagine, it's probably going to be what they did with the Room for the River thing. In Holland, I don't know if you know the story, the Room for the River done by Dirk Simons was really this decision, fundamental decision by the Dutch, which is a pretty big decision, to open the seawall. They opened the seawall because the threat was from the rivers of Germany coming in from the back and invading, flooding the whole city. So actually, major floods, and it happened again last spring, with a lot of people dying in Germany. When you get these major floods, you have to open to the sea, and you have to decide what gets flooded. I mean, it's more of a decision, to answer your question, Randy, it's going to be more a decision. Some of these rice paddies probably will end up being flooded, and others will be considered as islands. And of course, the salinity problem you're talking about is twofold. You have the briny water covering the field temporarily, but there's also the infiltration in the groundwater, which is a whole other story, tragic story in many, many places in the world. And that should be developing fairly soon too, with underground monitoring and modeling that could then be brought back in real time within a site model. If you have a space in question that you'd like to study, that would be the way to develop it. So what I'm saying is just, we're just developing. I'm not selling a ready-made finished product here. I'm saying this technique is a fundamental technique used in the whole world, from medical imagery to NASA interplanetary imagery. And it's really a very common technique, this three-dimensional pixel point imaging. And it's able then to generate topographical answers as well as climatic answers. And all this is developing very quickly. And what I imagine in Belipola is we could probably develop specific apps that make things simple. It doesn't have to be complicated. You maybe in Belipola, you just have 4 points of measurement that really give you then sort of it depends on how you derive the information afterwards. You don't have to scan every leaf and every tree. That's what I'm trying to say. I think the methodologies still need to be developed there.
Thank you. Thank you.
Very wonderful clarity. So the discussion has begun. Thank you, Ranil and Christophe. Originally, there was a question asked by Mr. Jayawardena, Amrik Jayawardena. Also regarding the technology, originally wasn't this technology from Chirax laser scanner geosystems? Amrik, are you here? Would you like to speak?
Hi.
Hello.
Can you hear?
Yeah.
Yes.
Go ahead.
Yeah. The question I wanted to ask the professor was, there was a technology of laser scanning that was invented for potholing, going into caves and scanning the caves so that you could understand where the caves went. So I was following this technology many years ago, and I think Leica Geosystems bought this technology from Cyrac. Is that correct?
Well, I'm not a member of the board at Leica, but I know that Leica has been definitely consolidating the knowledge. There's also Regal, this Austrian company. There's also Faro, the American company. There are maybe 3 or 4 companies doing that, but what you're referring to is clearly LiDAR technology. It's not geoposition. I mean, when you're underground in a cave, you can't relate back to the satellites. But if you peg the entrance of the cave, then you can really get your whole system georeference. And what I'm saying is it's a very widespread technology now, LiDAR technology. I mean, even the new iPhones and the iPads and all that have a mini LiDAR function. What I'm saying is it's becoming ubiquitous. I think the important thing for us as researchers and in order to protect and enhance nature in the future, it's going to become a very, very powerful monitoring and management tool. If it's used correctly, it's going to really, how could I say? Yes?
Yeah, at that time, there was a requirement for positioning 3 reflective globes, and that provided the reference from one frame, one point to another, of data acquiring. So the question I have is this laser harmful in any way in hitting a human eye? Or
no, that's evolved. The Leica Red were dangerous. They were category 2, but the latest devices are safe. So that's one thing. And then the other thing you're referring to is you need, of course, to get what you call a differential GPS. You need to have certain points clearly identified within a site, as a surveyor would do. A surveyor would mark with white paint or a circle or whatever it is on a rock or on a tree stump. You need to choose 3 or 4, like in Belipola, you would probably need 4 or 5 points that allow you then to snap your model into geographic reality. The absolute point given by the differential GPS allows you then to anchor the whole model into geographic reality. So it's not just the reflectors. The reflector is another thing. They're actually dangerous reflectors. We have a lot of avalanche surveying devices in the Alps with reflectors. When a reflector goes back directly into a laser scanner, it kills the laser scanner. You don't want to get reflection directly back into a TLS. But I don't want to get into the technical language right now, but you're right. It's evolving. I think a lot of companies are becoming aware of the importance of point cloud modeling as a tool. And I think it's going to become ubiquitous. 3-dimensional programs like Rhino have integrated that. Apple is integrating that in their devices. I mean, within 5 to 10 years from now, even Colombo will have a LiDAR plan. The real question is, once you have a LiDAR model or plan, what do you do with it? How do you work with it? And what are the methods? I think that's what's interesting.
So even there on the oxygen production of a forest through samplings taken of certain trees and tree girths to canopies from the air, a ratio based on that particular species. Could you extrapolate over large landscapes?
Well, I imagine with the proper scientific rigor and the right algorithms, certainly. I mean, what I think it has been the problem so far with the whole environmentalist movement is it's stayed pretty much stuck in what was a revolutionary method 60 years ago, the ArcGIS, the two-dimensional mapping overlay of geographic information. Most people have been stuck in this method that's existed for about 50 years. And I think that we're at the break of a new, or at the dawn of a new generation of researchers that are going to use three-dimensionally. I mean, just imagine, we've been talking about rainforest depletion, and we've been talking about biomass depletion, you name it, and nobody really works in cubatures, in cube. What is the cubature of a forest? You know, we're talking about the mass of a forest, of a canopy, maybe 2 or 3 layers. Right now, it's all just done in plan, and then you apply some sort of ratio on the colored surface, and that's it. I think what's really becoming revolutionary is you could develop sectorial research on biomass, on forestry, that would really then, of course, to answer your question, be extrapolated to a bigger system of hedgerows or forests or analog forests. But I think that kind of research still needs to be done and would deserve to be done in a place like Belipola.
Thank you. We have a few more questions to be answered in this regard of how we are going to integrate this into the ecological realm. So there's a question from Mr. Aberatna. Could you please explain what is the role a botanist or an ecologist would have in cloud point mapping of a tree-dominated landscape?
Okay, that's a very good question. I'll gladly answer that. I mean, as I said, the laboratory that we've set up, the LVML, I do with my colleague, Adrien Regame, who's an ecosystem service specialist. And she's been really applying that methodology to point cloud scanning. So what I'm saying is, for a botanist, for instance, what we call feature recognition, a point cloud is incapable of telling the difference between a rock and a tree. A point cloud model in and of itself cannot distinguish a tree from a building. It just can't. It's just points. It's just points in its specific position. But it's working on a sector. So it could be the neighborhood that I showed you in Singapore, but it could also be Belipola, or it could be the famous rice fields that Ranil Sindanayake was talking about. If you start really looking at a specific site and then you work on what I call feature recognition, like identifying the different tree species within the arboretum, tagging them, putting that information on it, limiting the plant to where it really is, both above ground and below ground, I think that would be a fantastic contribution to the field to really show how one can botanically map not only species, not only just an inventory of species, but actually to map also their function, daily function, nightly function. You have these little sensors that you can put on the trees that report back every day. It sounds like gadgets, but we're actually moving very rapidly into a world where, in a way, real-time information about a site like Belipola could be not only monitored, but managed.
Thank you. Also, there was another question, 3 questions leading to exactly where you stopped off from. So I'll come to Shirani's question later after that. Mr. Dharmakirti, you had 3 questions. I think if you want to.
Hi, good morning, Professor Christophe. Thank you very much for enlightening us about the technology. I have 3 long questions. Please bear with me. The first one was looking at the dynamic data that can be captured in a time series manner, if possible. Because for the forest farmers who rely on the understanding what are the most ideal spots to do planting of shade plantations like coffee, cardamoms, cocoa, etc., that needs to be planted under a tree canopy. would like to know about what are the spots that the sun penetrates through the top canopy and would hit the forest floor, and also the spots that has the highest moisture levels in terms of mist that flows through the forest. So if there is a way before planting to do a time series LiDAR survey in the night to know where the mist factors have basically flown through, and during the daytime where the sunlight spots have hit the ground, that will enable better selection of ideal planting spots. That's my first question. The second question I had for you, Professor, is that in the technology, is there a simulation capacity? Because I know Hollywood uses LiDAR to capture the data points of a particular area, and then they build 3D models and alter the views. But in terms of our ecological restoration projects, we may want to see over a time series period how trees are growing, which ones are growing faster, which ones are slower, and then see what the future potential canopy structure might become based on the relative growing speeds of the different trees, and to be able to model that tree graphically to show the full extent of the canopy cover at a point in the future. So that is to bring graphical software. The third question, I hope you can bear with me till I finish this, my third part of my question. And the third question is, and the final question is, in terms of the practicality of capturing the data, in terms of the equipment that you have worked with, whether it is the American equipment or the Swiss equipment or German, which is the equipment that gives you the maximum coverage with the highest resolution, and what is the square kilometer range that can be covered with the least amount of time and deployment of vantage points? Thank you.
Wow. So these are three very complete questions. So I'll try and remember them all in series. I'll answer the first question. You're absolutely right. I mean, this whole question of monitoring light and relative humidity and ground hygrometry, I think this would probably best be done by putting sensors. You know, you're not going to go out with a scanner every day and every night and try and scan things. You're actually going to create a framework, a sort of digital framework. The tree is there to stay. The trunk is there to stay, even a young tree. And based on that, then we can start extrapolating information. So I think to answer your first question about relative humidity and sunlight or light impact, I think that would need to be based on practice and understanding clearly what the reality is. So if you have, for instance, and these sensors don't cost that much, you know, the relative humidity sensors or light sensors, you can have, you know, 100 strewn through Belipola, and it would give you a very clear reading, depending on what kind of matrix you lay down on that particular piece of terrain. It could give you very, very precise microclimatic information. In my opinion, what you're asking here ties back to this whole question of researching microclimatics at Belipola using these modeling techniques. I think that would be really an area to develop much stronger, right? So that's, I don't know if that answers your question fully. I think the terrestrial laser scanner is a device to give you the armature, and then how you then go into specific localities. It can even be someone researching micro you know, algae and moss growth. I don't know where. I mean, you can really zoom in to certain areas and start working on very specific microclimatic qualities, you know. So I think that'll develop over time. The second question you have, which is about simulating growth into the future, the way we've done it so far is we've recognized certain tree species in point cloud, typical. We look for a typical tree and we scan it entirely, and we keep it in a sort of library of trees. And so we're able to estimate what a tree looks like in 30 years or 40 years. And you can literally implant, you can bring the tree in, right, and put it into the model, and then act as if it were done, right, as if it was there, right, which is this very complicated thing between the reality of the site and then the fiction, you know, how how we add in features into the site. I think that requires a very precise method, and we need to be careful not to falsify the model. That the original model remains the model, and then we're projecting time, T1, T2, T3, you know, whether it's 10, 20, 30 years, and that can definitely be developed. It would require, though, as a preamble, that one really documents the palette of trees we're working with. We have German engineers developing self-growing digital trees. I have a little bit of doubt about that. I'm not sure that's really the way you want to go with that. I would find it much more reliable simply scanning in point cloud an existing tree species, whether it's a mango tree or I don't know what, a jackfruit, and then putting it in. So I think that can work, and that's typically what we use workshops for. You know, we invite students. Like I imagine Belipola could be scanned in a summer school session by students. You know, within a month we could have the whole Belipola model pretty much scanned. And then we go into finer details, working on areas, developing areas, as you said, you know, where should you locate the coffee plantation in Belipola? That's all a matter of course, of a lot of factors, orientation, soil, humidity, you name it. So I think that's answering question 2. Then answering question number 3, in terms of the development or technology, I think that the technology that we're developing right now is there to stay. It's a standard system that's been developed, you know, on a very broad basis, the Lidar system. There's of course good Lidar and bad Lidar. There's highly precise Swiss Lidar, and there's less precise, I don't know what Lidar. You know, you have to be careful about how you're actually using this technology. But what I think is important to understand, and I think that's the main message, is we have always used a technology that can be used by a simple handheld telephone or laptop. I mean, if it's not manageable or doable on site or on terrain, and if it has to be stored in some sort of computer center in some big building in the city somewhere, it's not going to work. You know, we want to be able to work locally on site with that. I'm not sure I'm answering fully question number 3, but
No, Professor, thank you. But just going back to the question number 1, I understand yes, from a small scale perspective like me, Rahab, in the scanners on the ground to capture the microclimatic conditions. But when we are looking at a vast terrain where we have no accessibility per se to a vast forest terrain, to understand the sunlight penetration level to the forest floor, be able to read the point cloud data to look at the differentiation in terms of light. I don't know, there must be some sort of software model that can be worked out to identify which area of the forest floor has received more sunlight by doing a time series scan. It can be a 12 noon scan that gives us the maximum sunlight penetration to that forest floor on a clear day that we do the survey. Is that possible?
Well, as I said, you know, the whole of Switzerland is scanned in Lidar. It's just a little airplane with a Leica underneath it, and it just flies over. I certainly hope that Sri Lanka will be scanned. We can talk about that with the Swiss embassy, you know, maybe the Swiss could contribute to that. I think that you could scan the whole terrain. I don't think it would be reasonable for you to come in with a terrestrial laser scanner and try to scan the example I showed at the Israel-Jordan border is an exception. It would require much more skills. And Lidar would be the best way to go. You fly with the airplane, you cover a whole region, like Uva region would be scanned, and then you have that as a base, as a sort of reference base. And that's going to happen, you know, but that's what I would encourage. And then, of course, based on that, depending on the question you ask, the scientific question you ask, either you have enough resolution, usually the resolution is about 150 points per square meter in a normal terrestrial LiDAR. You know, we all grew up with Landsat. You know, you remember those satellite images and the famous infrared images. Now you have the whole hyperspectral realm that's coming in, and you can use drones. So in a way, what I would do is I'd use a LiDAR base, for the whole region, the big region you're talking about. And then based on the questions you'd have, I would come in with drones and hyperspectral cameras to really monitor what you're talking about. And that's all taking place. Like, you know, I showed you this drone that we have, this bird. We don't use it anymore. It's a dinosaur, right? It's prehistoric. Now the little drone, you know, Chinese have been building drones like crazy. They're becoming incredible surveillance equipment. I could imagine in a place that you research or in Belipola, you know, maybe there'll be, you know, 6 or 7 drones just flying permanently in the forest, monitoring and picking up data, coming home. You know what I'm saying? I mean, you can imagine how this information network is going to build up. And I think it's really going to happen in that way because the technology is following very closely there.
So I think Ranil may have told you, Professor, that we have a Green Climate Fund $42 million grant that we got to do a watershed restoration in the Knuckles in the Matale district. And that's a very unique geographical area of Sri Lanka. And so that's part of a project that starts with ICRAF being a technical advisor from the World Agroforestry Center out of Nairobi. And IUCN is also part of it as the accredited entity. So Ranil is an advisor and actually helped draft that particular project proposal. So that's an area, landscape level watershed with 2 rivers. And that's possibly an area that you could deploy this type of technology you're talking about. And the funding is there. And the funding is there. So it's a possibility to do that.
I mean, the LiDAR technology, I mean, I think we're talking about 2 very different things here. So I want to make sure we don't create confusion in whoever's listening. The framework for the big region, like a watershed of 2 rivers, you know, I could imagine scanning from the headwaters, the headlands, down to the estuary. I mean, you could do the whole river system in one LiDAR go. It could become a document where you literally catch the whole catchment. That's an airplane flight. It would probably take half a day and it would be done. You'd have that base model. Then the scientific question, you know, for instance, are you differentiating between the top canopy, the middle canopy, the lower canopy in the forest? How are you organizing that? I mean, as I showed in my, I mean, I was just cutting through Japanese houses, but I could cut through Sri Lankan jungles in the same way. I could cut the roof off the forest and show the middle canopy. You know, so you can start going into very precise levels of research. And I think we shouldn't confuse the big framework, which is the LiDAR campaign. And that obviously, you know, I saw that in Indonesia. I've seen that in Japan. It's been incredibly difficult getting LiDAR data of Kyoto, for instance. It's taken us 7 years. We finally got a LiDAR plan of Kyoto 3 months ago. It took 7 years. You know? So even in sort of you know, hyper-industrial superpowers, they're not able to do that. So what I'm saying is that it's interesting to understand how fast or slow people have been. I think the reason to explain why things have been so slow is that the engineers, the civil engineers especially, if I can say so, and I say that because I work with them very often, they've been a bit lazy. You know, they've used the old 19th century method. They use the LiDAR information, the point clouds, but they just extract a normal plan and section out of it. They get their height information where they want. They throw the rest out. It's like they throw 95% of the data out, and they keep the key points, you know, where the bridge is going to touch the edge of the mountain or whatever it is. So what I'm trying to say is I think that the big framework, I mean, in a research project like the one you're talking about, I would start, if I were to deploy, I would say the first thing we need to negotiate either with the government or the local authorities or the funding agency is a LiDAR campaign for that whole watershed. So that's the first thing I would ask for. And then depending on where your area of research is in focus, you come in with these other instruments and you get more precision and more attention. You're going to have to, as in any scientific method, you know, you need to find the right boundary conditions and all that, but you pick your points and then you develop points of information. And I even think that in Belipola, we're not going to be measuring every leaf and every moss around every step. That's not true. You know, you have to have very focused questions, and then the technology comes in and packs it in.
Thank you.
Thank you.
You're welcome.
Coming back to the session, is there any more questions? We have, can the technique be cross-referenced with existing data sets and satellite images to identify separate objects or tree species? So,
hi, that's Robin. Good afternoon. Thank you
Hello.
all so much. It has been
from Amsterdam.
mind-boggling. I have never come across this technique, and I'm speechless of the amazing images you have shared with us tonight. Yeah, to really focus it back to Earth restoration's intentions, desires, and applications of the technique. I know I live in Costa Rica. I know that this country has made a satellite map of the country on a high resolution detail. And my neighbor was part of the team that needed to write the algorithm to analyze the data and glue all the images together. And he said it was advanced to the level that they could identify different species within or different varieties, sorry, within tree species out of the satellite images, like 13 different types of ficus, for instance, in an area, which was also mind-boggling. So I was wondering if you could cross-reference GPS data with the images you provide or talk about to save your time, a lot of time in scanning, since these trees would be highly accurately known on which location they are. They just, that's also it from up in the sky.
No, I think that's a very good question. I mean, I think it'd be really wrong to throw away 50 years of environmental tools of analysis. I think they're there. I think that what I'm showing is a complement to the old GIS methods. What I'm trying to say, though, is I think it's important to understand that we're training, at least in Switzerland, we're training all the young students, whether they're environmental engineers or architects, they're trained in three dimensions. They're no longer working in zoning maps. They're really working in the physical realm. And I think that the information you're talking about, I mean, you know, I was trained on Landsat pictures and infrared, and we could already identify 40 years ago. I remember when I studied at Berkeley, the Landsat information was there. And by the way, the model we showed of Zurich, the colorized model of the whole of Zurich, was using a Landsat image put at scale on a Lidar model, right? So you can combine those two things, right? You can combine the color pixels on the geographic location and get away with it. I mean, it's not perfect because if it's from above, then the sides of the buildings or the sides of the trees are much less scanned than the tops. But that's the logic that we're in. I think that with hyperspectral cameras, and they're developing very quickly, you get a whole other range of information. It's not just about plant taxonomy and identifying 7 species. There it's literally about monitoring the physics of the plant. You know, evapotranspiration, you can probably get sensors of taking the sugar development, intake, release, you name it. And I think that that's really what's going to revolutionize. It's that this, we're going to integrate the GIS information you're talking about, of course, if it's accurate. It has to be accurate. If it's not accurate, then that's an open question. But if it's accurate, yes. And it just means that then we're going to go to the tree itself and start working around that tree and its roots. And I think the next big frontier would be mapping the root system in a forest like this, which will probably happen with sonar technology and other traces, you know, whether it's radioactive traces or whatnot. It's going to be a done reality very soon. It's going to happen. So what I'm saying is I think that we should not throw away the old stuff, you know, the older stuff. I was trained in that stuff, so I speak knowingly. I'm just saying we're still missing a lot of information on how a forest breathes throughout the day, how it transforms, how it produces biomass, etc. It's not just species identification. And in a way, the infrared photography was that. It was about, doing an inventory of tree species. I remember having to follow an infrared map with a magnifying glass and counting the number of trees that were there. The technologies are much faster now. Feature recognition is also developing much faster. And I think those are all applications that could be developed much further in a place like Belipola.
And I think that it was mentioned in the questions before as well. I was also highly curious on the budgetary needs for these different phases that you set out, starting with a big overall map and then going in. Like, what are we talking about with this technique?
Well, listen, for Japan, we rented just one. I mean, it's a totally different scale in Japan. It's using faro, very short scale, like 150 meter range devices. We would rent the device like that for $1,000 for a whole week. So that's what it costs, So what I'm saying is, and that was about 7 or 8 years ago. What I'm saying is the cost factor is not going to play a role. Like, for instance, Belipola would not have to buy all this equipment, probably rent it. I would strongly recommend renting it, maybe keeping a couple of house drones or house robots around. But the TL, once you've done your framework scanning with the TLS, you need it maybe once a year. You get the terrestrial laser scanner again, and that's it, So you don't need to be a fetishist, especially with the humidity and the problems with mold and everything. I would not recommend keeping a sort of object fetishistic array of equipment, because they tend to be obsolete after 5 years, like most high-tech products. I would just budget a rental, and I don't want to come out with numbers, but I mean, I don't think the cost factor is a limiting factor right now. What we find the limiting factor to be are a lack of trained people, people that are not able to operate within this realm. And that's what we're training through the workshops. And I think that, and that would be the idea also at Belipola, if we could start training younger people to be operational, whether it's at a doctoral level or a postdoc level, that would be great. I mean, we need to take this thing very seriously.
Amazing. Thank you so much.
Okay.
Thank you. I think you answered also a question whether the technology is going to be affordable. I think it's a question of strategizing towards it, and you answered that. So I really want to say, from the perspective of Belipola and conducting this session, that as a resource center concerned with futures and the ecology, it is a hugely potent position to be in. And the opportunity at Belipola is to share education. The resource center is now available to the public to engage with in terms of discussing these futures, integrating some aspect of modeling these futures into your designs in the current context, as well as bridging education at an international level. So I would like to say that this has been a really insightful experience, Dr. Christophe, with you. It's been wonderful, your patience, your simple articulation of great body of work that you have achieved and accomplished over time. And like the forest, we are very grateful. We are benevolent and grateful for you reaching out in this way. Today, we had a lot of participants from the Sri Lankan university networks, most of them from the landscape and architecture faculties. We had ecosystem restoration outfits from around the world, including from where Robin spoke, the UK, the US. We had local NGOs and private organizations who are developing their ecosystem restoration projects and could greatly benefit with this scope of education, this package really coming and landing itself at the rural climes of Mirahawatta. You spoke about rural development. I think it's a very soft and a very close topic to even Dr. Ranil Senanayake, who has been preaching about how rural development needs to be put in context of not marginalizing societies, communities, as well as the landscape. So if there are any more questions, we have this panel open for 5 more minutes. And then I would like you to please keep in touch via the Belipola network. Our website is on this chat window, belipolaarboretum.earth. We have a senior research fellow who is coordinating through the University of Peradeniya, Mr. Samira Aberatna. You can speak to him at any time, contacting Belipola, and we can also contact Professor Christophe at that time. Any more questions?
Thank you. Thank you, Dehan. I just wanted to add one thing. I think that environmental protection and development, or environmental planning and management, cannot happen, will not happen without educating people, without really training the right people. And I don't think it's the question of the cost. I don't think that we should say this technique only belongs to America and Switzerland and doesn't belong to us. It's readily available technology, and I really think that training young people in this field at this time, developing apps around management questions, monitoring questions, I think it's not only the right moment to do that, but it would be a great opportunity for Sri Lanka to take the lead in matters of environmental planning and management. So I can only encourage that.
Thank you, Professor. Really appreciate your support. Students, the forum, colleagues, please, this is your final 3 minutes to pose a question or say thank you.
I think we're good, Dehan.
Okay. Thank you very much, folks. So we'll end this session here. Please have yourselves a great day. Give appreciation to the breath. And let's hope that we can learn personally from Professor Christophe. Thank you.
Thank you, Professor. Appreciate it. Thank you, Dehan. Thank you, Ranil, for setting this up. Appreciate it.
Bye-bye. Thank you.
Bye-bye.